Since the beginning of 3D computer graphics, one particular shape has been used as the building block for rendering complex scenes and objects: triangles. These three-sided shapes are at the core of the vast majority of 3D video games due to their many interesting properties. It's the shape that can form a polygon with the lowest amount of vertices. They are both computationally and memory efficient, and all modern graphics cards are specifically designed to process triangles in parallel. Generally, the more triangles you can process at a time, the more detailed your 3D models and environments will be. Rendering all of these triangles on the screen is done through a process called rasterization, which comprises three main stages. In a first place, a vertex shader will transform the vertices of each triangle from 3D world space coordinates into their 2D screen space projections using the current camera position and orientation. The actual rasterization stage happens after this step and takes these screen space vertices in order to calculate which pixels of the screen, also called fragments, are actually part of the current triangle. Finally, the fragment shader processes each of these fragments to calculate their final color displayed on the screen. This part generally uses information from the vertices and external light sources to shade the pixel accordingly. This process is done for each triangle and for each fragment that needs to be rendered to produce a single frame. Of course, this is an oversimplification of the 3D rendering process. There actually exist many more stages in the rendering pipeline, and numerous optimization techniques have emerged to minimize the number of triangles and fragments processed at each frame. Since the advent of rasterization, the objective has always been to draw more and more triangles on the screen simultaneously for larger and more detailed environments. However, alternative 3D rendering techniques also exist, ones that don't necessarily rely on millions of triangles to create beautiful and complex visuals. This scene is currently being rendered in real time using a technique called Raymarching. All of the objects are generated procedurally, employing not millions or thousands, but merely 2 triangles. Let's count them. Here's the first one, and here's the second one. Using this technique, the vertex shader and rasterization stages become nearly insignificant in terms of performance, given the mere 2 triangles and 4 vertices processed per frame. Now, everything from the camera to the scene is calculated in the fragment shader stage for every pixel of the screen. But how? To illustrate it, I'll use this amazing shader made by Canada that explains how Raymarching works in shaders using Raymarching. I've also used it as a base to create a lot of custom animations that you'll see throughout this video. So, in Raymarching, the 2D screen will be projected into a 3D world directly inside a fragment shader. For each pixel, we calculate the direction of a ray that originates from a camera and that passes through the canvas. We can use these rays to calculate the intersection with the scene and colorize each pixel based on what they hit. The term Raymarching gets its name from the way it calculates the intersection between a ray and the scene. In contrast to ray tracing, which employs intersection functions to precisely determine where a ray hits a shape, Raymarching uses distance functions to gradually step and march into the scene until an object is hit. We can use them to calculate the distance to every object in the scene given a position in space. The distance to the closest one is used to safely march the ray in its current direction while being sure not to overshoot any object. This process repeats until the closest distance becomes arbitrarily small, indicating that we hit an object, or until the ray extends too far out, indicating that we didn't hit anything. This simple process allows the rendering of any scene or object that can be defined by a distance function, and it led to the creation of stunning worlds and effects that showcase the potential of this technique. However, despite its power, Raymarching is rarely used as the main rendering method in large-scale games. Even if we're rendering only 2 triangles, we still have to procedurally recalculate and render the entire world at each frame for millions of pixels, and the computations can quickly become expensive. Raymarching is more commonly used in video games on top of rasterization to render effects such as volumetric clouds or global illumination. This technique is also well suited for artistic purposes and mathematical renderings. It can lead to infinite creative possibilities, often in a few lines of code and in real time. In this video, I will be explaining how I created the following animation step by step, while introducing some important concepts related to Raymarching so you can start rendering your own 3D scenes. I will also share some useful resources at the end of the video if you want to learn more. This tutorial will be the building block for many of my next videos, as I will go deeper into techniques related to Raymarching, such as lighting and shadows, neons, volumetric rendering, terrain generation, 3D fractals, path tracing, 3D path traced fractals, and every other amazing technique that I'll get to learn through my journey in the shader realm. And remember that this is only the Raymarching branch of shaders. There exist many more concepts to play with. I couldn't emphasize enough how much anything's possible within shaders. From cellular automatas to neural networks, you can find a remake of Minecraft or a functional Apple I emulator. It really is a creative playground. Now, I will go to the Shader Toy website and I'll create a new shader. I'll remove the default code and replace it to display the UV coordinates in clip space, as explained in my first video. I highly encourage you to watch it as I explain the very basics of shader programming and the GLSL language, and won't go into as much detail for the steps that I've already covered. Now let's delve into the practical steps of Raymarching. In traditional rasterization, we usually define the camera and objects beforehand and send them as inputs to the rendering pipeline. But here, we have neither a camera nor objects as we're directly working inside a fragment shader, so we'll have to create them for each pixel. The very first step consists of creating a ray origin and direction for each pixel. In order to do so, let's enumerate some constants first that will help us represent objects in our world. We will use 3 component vectors to denote points in 3D space, and the world's origin is the point located at 0, 0, 0. We also need to define 3 orthogonal axes that will form the basis of our vector space. For simplicity, let's define the x and y axes of our world so that they align with the canvas's x and y axes represented by our UV vector. Consequently, the additional z axis will represent the depth from the canvas. Note that we don't actually need to define our origin or these vectors in code. We only need to visualize them and know what they are to allow for a more intuitive way to build and interact with the scene. With that in mind, let's define the ray origin vector. It corresponds to the camera's current position in our world. For our initial setup, let's place it 3 units behind the origin along the negative z axis. Let's now create a vector to represent the current pixel's ray direction, initially pointing straight in the z direction. Since all rays originate from the same point, giving them the same direction would result in them following identical paths and having the same color. To make each pixel's ray unique, we can leverage the UV vector, which is in clip space, directly as the x and y components of our ray direction. This works because we've decided earlier to align our world's x and y axes with our UV coordinates. This modification will make each pixel have a unique ray direction spreading out from the center of the screen and effectively creating a virtual canvas to project the world to. Finally, we need to normalize the ray direction. Normalization scales the vectors to ensure they all have a length of 1, which is crucial for accurate distance calculations in the next step. Now, let's introduce a float variable to keep track of the current distance our point has traveled from the camera's origin. This distance will increment with each step, starting from 0, and will ultimately store the accumulated distance traveled by the ray across the world. Creating a ray origin, direction, and travel distance can be seen as the initialization process, and I'll indicate it with a comment. The next part will involve the actual Raymarching. We are going to define one step of the algorithm that will then be iterated using a loop until an object is hit. Now, our primary interest lies in determining the position of the current marching point rather than just its distance from the camera. Luckily, calculating the position at each step is straightforward using our current variables. We'll define a new point called P that will be located at the ray's origin and add to it the ray direction times the current distance traveled. This gives us a 3D point representing the current position along the ray based on its distance from the ray's origin. We can then use this point to compute the distance to the closest object in the scene. Note that it actually starts at the ray origin as t is initialized to 0. To do so, we will use signed distance functions, also called SDF. These functions can be used to obtain the distance from a given point in space to a particular shape in the scene. I would highly recommend you to check out this article written by the master of shaders Inigo Quilez that provides some useful distance functions and tricks related to Raymarching. So, to define the objects in our scene, we will create a function that takes a 3D point as input and returns the distance to the nearest object in the scene. We'll come back to it later, and for now, it will only return the distance to a single sphere of radius 1 located at the origin. We can then use this function to get the distance to the scene given our current position along the ray, which I will store in a new variable. This value represents the safe distance the point can travel to in any direction without overstepping an object. Finally, we need to add this distance to the variable that keeps track of the total distance traveled from the ray's origin. This is the step where we march the ray. We can repeat these steps by encapsulating this code within a for loop, with the variable I representing the current iteration or Raymarching step. For now, I'll set it to a maximum of 80 iterations. This number affects both the quality of the result and the performance. Too few iterations might result in rays not having enough iterations to reach an object, while too many can significantly impact shader performance. Typically, you'll need to adjust this parameter to suit your specific scene. In summary, for each pixel we start by initializing a ray origin, a ray direction, and a travel distance. These parameters help us calculate an intermediate 3D point representing the current position along the ray. Since the distance is initially set to 0, the point starts at the ray's origin, which is the camera's position. From this position, we calculate the distance to the closest object in the scene, which is used to safely march the ray forward. We then repeat this process until we either hit an object or exceed the number of Raymarching steps we've set. And with this code, we're just one line away from displaying our first 3D object on the screen. I will create a new vector that will contain the current pixel's color and make it the new output of our shader instead of displaying the UV coordinates. Now, the easiest way to visualize something in a ray-marched scene is to colorize pixels based on the total distance traveled by the ray, which is stored in the variable t. I will assign this value to the red, green, and blue components of our color vector to create a grayscale image. As a reminder, the shader's output color ranges from 0 to 1. Therefore, as soon as our ray travels a distance greater than 1, it will be displayed as white and we won't see any variation, which is currently happening since the camera is 3 units away from the origin. To address this, we can either move the camera closer or divide the distance variable by an arbitrary number to start seeing details further away. And there you have it. The unit sphere that we defined in the map function is currently being rendered using Raymarching. What we're observing can also be referred to as a Z buffer or depth buffer, as each pixel's color represents the distance from the camera to the scene in grayscale value. Before we continue, let's optimize this code to prevent our graphics cards from performing hundreds of unnecessary calculations, which they'll very enthusiastically do if not constrained. For instance, each ray currently goes through the entire 80 iterations, but in reality it can take far fewer iterations before the distance increase for any consecutive ray becomes too small to see a difference. Let's visualize it. Instead of assigning the output color based on the distance traveled, I'll display the total number of iterations that happened. I'll divide it by 80 in order to map the value to the 0-1 range, from black to white. As expected, all pixels display a white color, meaning that they went through the entire 80 iterations. So let's add an early exit condition to the Raymarching process. This condition instructs the loop to stop if the current distance to the scene becomes smaller than a certain threshold, let's say 0.001. You can experiment with different values for this parameter, but if you set it too high, the ray may stop too far away from an object's surface, leading to less precise shapes. On the other hand, if it's set too low, the performance gain may become negligible. With this modification, we can now see that the rays which actually hit the sphere don't go through the entire 80 iterations, but a way smaller count given their shade. However, the other rays will continue through the full 80 iterations, extending dramatically far into the distance. To put things in perspective, I've written a small JavaScript function that calculates for each step the distance traveled by a ray that barely misses a sphere. For the first 14 steps, it doesn't go further than 10 meters away from its starting point. But then, things start to take an exponential turn as only 8 steps later we're going past the kilometer mark. And once we've reached the 40th iteration, the ray has nearly traveled the distance that separates Earth from the Moon. Finally, at the end of its trip, 80 iterations and 36,000 light-years later, the ray would have traveled a third of the Milky Way at speeds that general relativity cannot comprehend. It's highly unlikely that we'll need to visualize objects at such extreme distances. So let's add another exit condition that halts the loop if the current distance traveled by the ray exceeds a certain value. We don't need to calculate this distance precisely given how fast the ray exits the scene. Instead, we can set it reasonably far away to ensure that objects in our scene won't get clipped or cut off prematurely. And as a result, we can observe a significant reduction in the iteration count for rays that don't hit the sphere. Let's now group these two optimizations in one single line and go back to showing the depth buffer instead of the iteration count. We've finally reached the point where we have our fundamental Raymarching algorithm, which can be very similar to a blank canvas in a 2D case. It serves as the starting point from which I typically begin to create, explore, and experiment with Raymarching. And you can find this shader in the description. There are many concepts, techniques, or hacks that can be used together to create mesmerizing scenes, and I'll demonstrate a few. Our attention will now be directed to the map function that we defined earlier. To make things clearer, I will create a new variable containing the distance to our sphere and call a function that computes its signed distance. Let's start by exploring translation. We have the ability to manipulate the positions of objects in our scene by adjusting the input position that we send to the distance functions. Let's introduce a new vector that represents the sphere's position in our 3D space initially set to 0. I will subtract this vector from the input position before sending it to the SDF. Now it is possible to move the sphere in the scene in all three axes that we've defined earlier by adjusting this vector. For example, let's move the sphere 3 units in the positive x direction. This calculation may seem a bit counterintuitive as we actually need to subtract the vector in order to move in the positive direction. To understand why, let's visualize what happens to the ray's direction during a translation. When we perform the subtraction as described, we're essentially shifting the ray 3 units in the negative direction, resulting in a movement to the left relative to the world. But if we replay the same animation relative to the ray itself, you'll notice that it seems as if the scene is moving in the opposite direction, from left to right. This explains why translation and other transforms will usually appear inverted in shaders. Finally, it's very easy to add real-time movements by including the current time in the object's position. In this case, I use a sine function of time to make the sphere's x position fluctuate between -3 and 3. As a quick note, the distortion we're observing when the sphere approaches the edges of the screen is inherent to perspective projection, which we're implicitly using. This distortion is connected to the camera's field of view, which indicates the total angle covered by the rays. A larger field of view lets you see more of the scene simultaneously, but also intensifies the distortion. If you'd like to control the field of view, you can multiply the x and y axes of the ray direction before normalization to influence how the rays are spread. Now let's add another object into the scene. I will define a cube of side point 75 located at the origin. In order to combine these shapes, we simply have to return the minimum between the two distances using the min function. You can think of this line as an operation that unites the two shapes, also called the union operator. If you want to get creative, you can experiment with other operators like the difference or intersection operators to combine shapes in more interesting ways. Additionally, there are smoother versions of these operators that allow for a gradual blending between the shapes. I'll use the smooth minimum function, which includes an additional parameter for adjusting the blending, allowing us to create a smooth union between these shapes. Finally, I will quickly add a ground by creating a new variable that holds the signed distance function to the xz plane, which is quite easy to calculate. Let's visualize one ray coming out of the camera. The distance between any point along this ray and the ground is directly determined by the ray's current y position, which represents its height above the ground. I will also push the ground further down by adding an offset of 0.75 to its distance. Otherwise, we won't see anything as the camera would be at the exact same height as the ground and intersecting with it. Once again, we add a positive number to move the ground in the negative y direction. It's also possible to smoothly union the ground with the other shapes. This time, I'll use a lower blending amount. Another transformation that we can easily apply is scaling. While these two shapes can actually be resized using their input parameters, scaling remains a valuable operation for more complex or grouped objects. To execute the scaling operation, you simply need to divide or multiply the input position. Much like the translation operation, the resulting size change of an object is inversely proportional to the scaling factor. However, scaling actually distorts the metrics and distances within our scene, unlike translation, which can introduce artifacts in the rendering. To address this, we need to counteract the scaling effect. This involves multiplying the final result of our distance function by the inverse of the scaling factor, or in simpler terms, dividing the output by the scaling factor. This adjustment ensures that distances in our scene remain accurate and removes artifacts. As a final note, here I've made the scaling uniform, but you could also multiply the position by a vector in order to apply a different scale factor for each component. I'll remove the scaling on the cube, and now I'll introduce the last basic transform that we can apply, which is rotation. This one generally involves the call to an external function as it requires a bit more math. To rotate a point in space, you need to multiply it by a 2x2 rotation matrix in the 2D case or a 3x3 rotation matrix in 3 dimensions. As you can see, there's a gap in the complexity of the computations when adding another dimension. Fortunately, in the 3D case, there exists a simpler alternative called the Rodriguez rotation formula, which achieves the same result without using matrices. I won't go into the math behind these functions, but I'll link in the description some resources if you want to get a better understanding about vector rotation. Let's start with the 3D scenario. This function takes as input a point in space, an axis, and an angle of rotation in radians. The axis is a vector representing the 3D line around which the object will rotate, and it must be normalized. We can use it to rotate objects in any direction, but I often prefer using 2D rotation functions even in 3D scenes, the main reason being their speed and simplicity. However, this function only operates on vectors of 2 components. In order to use it, we'll need to extract 2 components of our 3D point using swizzling syntax. This constrains the rotation to be around the 3 fundamental axes only, but it can be chained around multiple axes to allow for a greater range of rotation. Once you can visualize the 3 primary axes in space, using this function to rotate objects becomes quite straightforward. In the swizzling syntax, the component that is omitted represents the axis around which our object will rotate. To demonstrate it, I will create a copy of the input position in order to rotate that copy only, and pass it to the box distance function. If I wanted to rotate the box around the z-axis, I would exclude the z component in the swizzling syntax and write q.xy. I can also use time to animate this rotation. Now, one aspect that is crucial in Raymarching is the order of operations. If you translate first and then rotate, you'll get a different outcome compared to rotating first and then translating. This rule applies to most transformations in Raymarching, so if something isn't behaving as expected, double-check the order in which you apply the operations. It's also important to understand that when we apply a transformation to the input point, it maintains that transformation for all future distance functions. This is why I've created a new variable to rotate only the box. If I were to remove this temporary variable, you'd notice that the ground also starts rotating. However, the sphere, which is defined before we apply rotation, retains its original movement. Now, it would be even better if we could add mouse control for the camera to view the scene from different angles. This can easily be done using the 2D rotation function I introduced, along with the current position of the mouse, which is accessible on ShaderToy through the iMouse global variable. It's a 4-component vector where the first 2 components represent the current pixel coordinates of the mouse, much like the fragchord input parameter. The last 2 components contain information about the starting position and state of the mouse, but we're only interested in the mouse position here, which we can extract using the .xy syntax. To get the mouse position in clip space, I'll create a new vector by applying the same transformation as our UV coordinates, ensuring they are in the same range. This new vector will have a value of -1 when the mouse is at the bottom left, 1 at the top right, and it will be 0 when the mouse is centered. Next, let's rotate both the ray's origin and direction around the y-axis. The rotation angle will be determined by the current x position of the mouse vector, which needs to be negated. If you now click on the canvas and move your mouse, you'll observe that you can rotate the camera around the scene horizontally. To grasp the mechanics behind this, let's visualize what happens when we rotate the ray origin only. You can see that the camera indeed rotates around the center of the scene, but it's always pointing in the same direction. This is why we also need to apply this rotation to the ray direction. When combined together, it will make the camera rotate around the scene while always pointing at the origin. For a complete 360-degree rotation around our scene, we can apply the same technique along the x-axis, this time using the vertical position of the mouse. The order of operations matters, and it's important to place it before the horizontal rotation. You can also scale the mouse vector to control how sensitive the rotation is. Now, let me introduce the concept of space repetition, which is an extremely powerful tool in Raymarching which allows you to render an infinite amount of shapes while defining just one. Similar to my previous explanation of space repetition, we can employ the fract function to replicate objects in space. This function returns the fractional part of the input for each component, keeping the result between 0 and 1. To visualize what happens when we pass the ray through this function, let's consider a 2D scene defined by the SDF of a box. The white line represents a ray as we previously defined it. Here it's starting very close to the box but not intersecting with it. The yellow line represents the same ray after going through the fract function. While the original ray remains unaffected by this transformation, the input to the SDF is always constrained within the unit cell at the origin. From the ray's perspective, this makes the scene appear to contain an infinite number of cubes, each one unit apart from the other. To achieve more granular control, it's possible to use the mod function instead, which takes an additional parameter that can be used to control the spacing between each repetition, fract being a special case of the mod function. Note that the current visualization is missing an important step as the cube is originally located at 0, while the center of repetition is located at 0.5. This makes every cube extend further than the repeated cell boundaries, and it results in them being clipped. This is why we also need to subtract 0.5 after applying the space repetition function. This translates each cube to the center of its cell and fixes clipping issues. Finally, I'll scale down the cube because it currently has a bigger side length than the distance of repetition, which makes it fill the entire space. And using this simple technique, we have achieved infinite space repetition in all 3 axes. The render is only limited by the maximum iteration count and distance limit set earlier. Note that it would also be possible to apply space repetition to individual axes instead of all 3 of them. Moreover, we can lower the intensity of the depth value to see further away, as the colors are still clipped above 1. We could also add an upward movement to every box by offsetting the Y position of our point before applying space repetition. Once again, if we were to add it afterwards, the boxes would clip out of their repetition. And now that we've covered all of these topics, we can start to get creative with our scene. I will start by removing everything from the map function apart from the repeated box, to which I will add a movement in the Z-axis towards the camera. So far, we've seen how to make a Raymarching algorithm and how to play with objects in our scene, but it's still colorized using the depth to the scene, which is a bit boring. The next easiest way to colorize objects is to pass the depth value as the input to a color gradient function that can convert this linearly increasing value to a color vector. I introduced a handy one in my previous video that can be tweaked to produce many different gradients, so I'll use it again. Let's go back to the colorization part. I'll call the palette function to calculate the output color and pass the depth as input. And with this one simple line, our previously monochromatic scene takes a whole new dimension to it. I will now replace the box distance function to the one of an octahedron because I find this shape more interesting and it's also a bit faster to compute. I will also decrease the spacing in the Z direction to make each shape closer together only in the axis that is parallel to the camera. For that, I'll decompose the space repetition in 2 parts. The X and Y axes will be repeated using fract as before, and I'll use the mod function with a spacing of 0.25 for the Z axis. I also need to offset it by half of the repetition spacing, which is 0.125 in this case. Now, you may notice that the current colorization technique makes the objects appear very flat as we didn't implement any lighting or occlusion effect. A quick solution would be to incorporate the iteration count from the loop into the palette function. This value actually contains information about the scene, as it will increase with distance but also increase when approaching edges of objects as it will need more steps to travel the scene. If we extract it from the loop and display it directly after normalizing it, we can see how much information it contains. This is only a hack because the iteration count is not smooth as opposed to the depth buffer. The lower the iteration count, the more visible the artifacts will be. This is why I will multiply it with a very tiny number, so the addition stays subtle. I also need to use the float keyword to convert it from integer type to floating point type. The change is tiny, but adds a lot to the depth of the scene in my opinion. To add a dynamic touch, let's start to distort the scene using the sine function. Like we've seen earlier, we can apply transformation to the ray itself in order to affect how objects appear in our scene. In this case, I will add a sinusoidal offset to the Y component of the ray, which will distort the scene in a unique fashion. I'll add this effect in the main loop before the map function to indicate that it's a scene transformation and not object specific. So I'll add the sine function to the y component of the position along the ray, and the frequency will be determined by the total distance traveled so far. I'll also scale down the amplitude of the waves for a cleaner effect. It's starting to look very interesting, and remember that our scene is actually still defined by a single undistorted octahedron located at the origin. It's just our rays that were given superpowers to completely ignore the rules of 3D Cartesian space and somewhat hallucinate new geometry. Next, I'll completely remove the camera rotation code, as I found it more interesting to control the frequency of the wiggles using the vertical component of the mouse. I want it to be going from 0 to 1, so I need to remap the Y component accordingly. This allows me to change the frequency of the oscillations by moving the mouse up and down. Now, I will use the same distortion principle this time, not to control the offset, but to control the rotation of the ray position. I'll go back to the previous visualization, and this time I'll draw 4 rays instead of just 1. I want these rays to start rotating around the z-axis the further from the camera they go. This can be done using the previous 2D rotation function. Like I explained earlier, as I want the rotation to be around the z-axis, I will extract the x and y components of the point. The rotation increases with distance, producing this stunning spiral effect that demonstrates once again how mesmerizing yet simple mathematics can sometimes be. Note that these two transformations actually break the distance calculations, similar to the scaling operator. If you distort the space too much, visual artifacts will start to appear. Finally, I can use the X component of the mouse to control the frequency of this rotation. I won't remap it here, so it ranges between -1 and 1 from left to right, allowing me to change the direction of rotation. When combined with the vertical movement of the mouse, it's possible to explore various and interesting twists for this scene. As a last step, I found it to be particularly interesting when moving the mouse in a circle around the canvas with this setup. So when the mouse is not pressed, I'll add a default behavior that simulates the mouse going in a circle motion. This is straightforward using trigonometry. The position of a point along a circle given a radius and an angle is the following. As we're in clip space, the radius is 1, and I can simply use time to have an infinite looping rotation. Let's add it to the code by overriding the value of the mouse vector when the mouse is not pressed, which we can detect by checking if the z component of iMouse is negative. This addition will fake an endless circular motion of the mouse around the canvas to give a final touch of dynamism to the scene. I believe that now would be the appropriate time to sit back, take a break from the code, and appreciate the journey that started from a blank canvas and led to this intricate world. We can now immerse ourselves in this mesmerizing scene as the different parameters evolve and synchronize in real time to produce beautiful geometric patterns. There's so much more to cover, but I hope this gave you enough foundations to start playing with Raymarching and become a ray bender yourself. The door is now open to many interesting 3D rendering techniques that I will cover in some of my next videos. If you want to support these tutorials, I've created a Patreon that I will use to share updates about what I'm working on and ask you for what you'd want the next video to be about. In the meantime, if you'd like to learn more about Raymarching, I would suggest exploring the Art of Code's channel. Specifically, his Raymarching tips and tricks video lets you discover alternative methods for twisting space and how to address some common Raymarching artifacts. Moreover, if you happen to have some free time, watching the replays of Inigo Quilez's live coding sessions can be incredibly enriching too. I gained valuable insights from these sessions that I believe can serve as a fantastic learning resource for you as well. Happy creative coding, and see you in the next one.